This video goes through how to find a general solution for a trigonometric equation. Now, when solving a trig equation over an unrestricted domain, meaning we're not given a domain, infinite solutions exist because we can keep going around our unit circle. So every time we do another revolution, we get another two solutions. Now, you can write the solutions in general form by considering the positions of the coterminal angles and remembering every time we add 2 pi to our initial solutions, so in that first revolution, we end up in the same spot, so that's also a solution. So what we do, if we had solve sine of x equals a half, normally we would go, what's our reference angle? So our reference angle is equal to inverse sine of a half, and that's pi on 6. We then would go sine x is positive, so we know we're in our first and second quadrants. So our angles would be x equals pi on 6 in the first quadrant and pi minus pi on 6 in the second quadrant. So that's pi on 6 and 5 pi on 6. So that's how we would normally solve. For the general solution, we know we can go 2 pi and end up in the same spot. So our general solution for pi on 6 would be pi on 6 plus 2n pi. And for the 5 pi on 6 plus 2n pi, where n can be any integer, meaning it could be negative going in the negative direction, or it can be positive going in the positive direction. So if n equals 1, we add 2 pi, that's in the next rotation. If n is negative 1, we go in the negative direction. And that's all we have to do. So our general solution is x equals pi on 6 plus 2n pi, and x equals 5 pi on 6 plus 2n pi, and n is an element of z. Now, in your textbook, it does combine these into one solution, and there's a general formula. I'm personally not a fan of using a formula for these. I would just do them like this every time. So our general solution for sine will be x equals theta plus 2n pi, and x equals pi minus theta plus 2n pi, where n is an element of z. And again, you can look in your textbook for combining that into one. Now, cos x equals the square root of 3 over 2. So our reference angle would be inverse cos of the square root of 3 over 2. So that is pi on 6. Cos x is positive, so we know we're in our first and fourth quadrants. So we would normally go x has to be pi on 6 and 2 pi minus pi on 6. So that's equal to pi on 6. 12 pi on 6 minus pi on 6 is 11 pi on 6. Now the key with cos is we have pi on 6 and negative pi on 6. So if I add 2 pi to the pi on 6, I end up back to here. If I add 2 pi to the negative pi on 6, I'll end up back there. So I can combine for cos into one general solution, and that would just be plus or minus our pi on 6 plus 2n pi, where n is an element of z. So for cos, our general solution will always be x equals plus or minus theta plus 2n pi, where theta equals our reference angle and n is an element of z. So let's finish by looking at tan. So my reference angle is equal to inverse tan of 1 on root 3, which is again pi on 6. Tan is positive, so we're in our first and third quadrants. So normally when we weren't doing a general solution, we'd just go x is equal to pi on 6 and pi plus pi on 6 for our third quadrant. So pi on 6, 6 pi on 6 plus pi on 6 is 7 pi on 6. And that's what we'd do if we didn't have a general solution. But our general solution is we keep going around. Now the key with tan is if you think about this, this is pi on 6. And in our fourth quadrant, we have pi on 6, which is how we get that answer being pi plus pi on 6, which is 7 pi on 6. Now, the key is this is a straight line here. Okay? And also thinking about your tan graph, your period is pi. So my general solution for tan can also be combined into 1, where x equals pi on 6 plus n pi, rather than 2n pi. So our general solution for tan will always be x equals theta plus n pi, where n is an element of z, and theta equals our reference angle. So let's look at some examples. Pause your video and have a go at these yourself. First, for sine, our reference angle is inverse sine of root 3 over 2, and that is pi on 3. So my general solution are going to be pi on 3 plus 2n pi, or x equals pi minus pi on 3 plus 2n pi. So that's 2 pi on 3 plus 2n pi, where n is an element of z. So n is an integer. For tan, my reference angle is inverse tan of 1 on root 2. That is not an exact value, so make sure your calculator is in radians. And you're going to go inverse tan of 1 divided by a square root of 2, which is approximately 0.62. So our general solution for tan is x equals our reference angle, should put approximate, plus n pi, where n is an element of z. Looking at the next one, which is cos 2x equals 0. So my reference angle is inverse cos of 0. Now, cos is my x coordinate, so that happens at pi on 2. So note for my general solution, I don't have to find the first and fourth quadrant. So for cos, I would go 2x is going to equal my plus or minus my reference angle plus 2n pi. So x has to be equal to plus or minus pi on 4 plus n pi. So I'm just dividing everything by 2, and n is an element of Z.